This slide introduces Section 5, Capacity Planning and Management, focusing on how organizations ensure they have the right resources to meet demand. We'll begin with Chapter 5.1, which covers the resource and capacity planning hierarchy, the framework used to plan capacity from long-term to short-term levels. This slide explains capacity planning, which ensures that a company has the necessary resources, machines, people, space, and materials needed to meet its production targets. Capacity planning answers three critical questions. How much can we produce? It determines the production capacity. When can we produce it? It helps in scheduling production. Do we need to add or reduce capacity? It helps in adjusting resources according to demand. Effective capacity planning ensures the smooth and efficient running of production processes. This slide shows the hierarchy of capacity planning. Resource planning 3-5 years uses strategic capacity plan for long-term facility and capital decisions. Rough cut capacity planning 6-8 months linked to MPS to validate production feasibility. Capacity requirements planning 1-6 months uses work center schedules to balance load versus capacity. Input, output control and dispatching days weeks focuses on short-term execution with shop floor control. Example, in pharma, capacity planning ensures equipment meets demand for a new drug launch or if a new line is needed. This slide explains key terms related to capacity measurement. Design capacity, the maximum output the system can theoretically achieve. Effective capacity, the capacity adjusted for factors like maintenance and breaks. Actual output, the real output the system achieves. Utilization is calculated as utilization equals actual output, design capacity, times 100. Utilization equals design capacity, actual output, times 100. Efficiency is calculated as efficiency equals actual output, effective capacity, times 100. Efficiency equals effective capacity, actual output, times 100. Example, for a machine with design capacity of 1,000 units day and an effective capacity of 810 units day, the utilization is 81% and efficiency is 90%. This slide compares rated capacity and demonstrated capacity. Rated capacity, it's calculated as planned hours times utilization times efficiency. This is the expected or theoretical capacity based on the planned resources. Demonstrated capacity, it's based on actual performance over time. This shows how the system actually performed in real conditions. Mini case study, Siemens uses demonstrated capacity data from their MES manufacturing execution systems to plan maintenance windows more accurately, which improves machine reliability by 15%. This slide explains the purpose and inputs of capacity requirements planning (CRP). Purpose of CRP. CRP checks if the planned orders from the MRP material requirements planning system can be produced with the available work center capacity. CRP inputs, planned order releases. These come from MRP, including the operations sequence and time. Routing data. This provides operations sequences and times. Work center capacity, the available hours for each work center. Shift patterns and efficiency rates, these factors affect available capacity and performance. Purpose of CRP. CRP ensures that the planned orders from the material requirements planning MRP system can actually be produced with the available work center capacity. CRP inputs, planned order releases from MRP. Includes operations sequences and time. Routing data specifies the required operations and their durations. Work center capacity, the available working hours for each center. Shift patterns and efficiency rates, these determine the real capacity available for production. This slide discusses the benefits of capacity requirements planning. CRP prevents overloading bottlenecks, ensures no work center is overloaded, improving smooth production flow. Enhances on-time delivery by managing capacities. CRP helps deliver orders on time, improves labor and machine planning, optimizes resource usage by aligning labor and machine capacity with demand. Mini case study, Bosch. After integrating CRP with SAP, Bosch successfully reduced urgent outsourcing costs by 18%. This demonstrates how effective capacity planning can reduce unnecessary external costs. This slide compares infinite scheduling and finite scheduling. Infinite scheduling, assumption, unlimited capacity. Speed, fast but less accurate. Use case, strategic or high-level planning. Drawback, can cause work center overload due to not considering actual capacity limits. Finite scheduling, assumption, limited capacity. Speed, slower but more accurate. Use case, detailed, execution-level planning. Advantage, more realistic and shop floor friendly, avoids overloading. This slide provides an example and case study to explain the practical application of finite versus infinite scheduling. Example, an MRP run generates orders that exceed the press shop's capacity by 30%. Finite scheduling then reschedules the orders to the next available time slot, ensuring that the work center isn't overloaded. Mini case study, Toyota. Toyota uses finite scheduling linked with Kanban. This ensures that no order enters production unless there is available capacity, avoiding any overloading and maintaining efficiency. This slide introduces bottleneck management and theory of constraints talk. Identifying bottlenecks. A bottleneck is the resource that limits the overall output of the system. It's the slowest part in the process. Symptoms of bottlenecks. Look for signs like queues, delays, or accumulation of work in progress (WIP) as indicators of bottlenecks. This slide explains the theory of constraints talk. Steps to manage bottlenecks. Identify the constraint. Find the bottleneck that limits throughput. Exploit the constraint. Fully utilize the bottleneck with no downtime. Subordinate others. Adjust other processes to support the bottleneck. Elevate the constraint. Increase capacity of the bottleneck if needed. Repeat the cycle. Continuously improve by revisiting the steps. Example, if a paint booth can handle only 40 units a day but upstream can produce 60, schedule all operations to align with the bottleneck to avoid overproduction upstream. This slide explains buffer management and its role in bottleneck management. Buffer management, it involves maintaining time or inventory buffers before the bottleneck to prevent starvation, waiting for parts, and ensure a smooth flow through the system. Mini case study, GE Aviation. GE Aviation applied talk to its engine assembly line, resulting in 28% reduction in lead time. Increased throughput without additional capital investment. This slide discusses key performance indicators. KP is for measuring capacity performance and improvement. Utilization, formula, actual output, design capacity. Purpose shows the percentage of capacity being used. Efficiency, formula, actual output, effective capacity. Purpose measures how effectively the process is running. OEE, overall equipment effectiveness. Formula, availability times performance times quality. Purpose, a comprehensive metric that evaluates equipment performance. Throughput, formula, units/hour. Purpose, measures the flow rate or output per unit of time. This slide focuses on continuous capacity improvement. SMED, single-minute exchange of dies, reduces setup time, increasing machine availability. Preventive maintenance ensures higher equipment availability and reduces unplanned downtime. Cross-training operators increases workforce flexibility and helps balance capacity across different operations. Data-driven capacity monitoring uses IOT dashboards to track real-time performance and optimize capacity. Mini case study, Tata Motors. By implementing OEE monitoring and Kaizen projects, Tata Motors increased line efficiency from 78% to 88%, adding 10% extra capacity without any capital investment.